Somewhere out past the orbit of Jupiter right now, moving away from us faster than almost anything humanity has ever tracked, there is a visitor that arrived from outside our solar system with no history we can trace and no way of ever coming back. And the first proper look anyone ever got of it did not come from a giant new observatory built for exactly this purpose. It came from Hubble, a telescope that launched in 1990, aging and remarkable in equal measure, pointed at a target nobody had planned for, doing exactly what it has done for more than 3 decades, catching something enormous before anyone else even understood what they were looking at. What Hubble found, and what a chain of telescopes after it confirmed, would turn one comet into one of the most intensely studied objects in the history of astronomy. This is the story of that discovery, why it mattered so much more than a typical comet sighting, and why scientists are still arguing over exactly what they measured. The story begins on July 1st, 2025, at a modest observatory in Rio Hurtado, Chile, run by a survey system called ATLAS, short for the Asteroid Terrestrial Impact Last Alert System. Its entire purpose is to scan the sky night after night looking for anything that might be heading toward Earth, cataloging thousands of faint moving points of light, and comparing each one against everything already known to orbit our sun. On that particular night, it caught a faint point of light moving in a way that did not match anything in its catalog of known asteroids and comets. Within days, astronomers around the world had confirmed what the object's orbit was telling them. It was not looping around the sun the way every comet and asteroid native to our solar system does. It was moving on a hyperbolic path, a wide-open trajectory that only makes physical sense if something arrived from outside the sun's gravitational influence entirely and is simply passing through on its way to somewhere else. It was given the name 3I/Atlas. The letter I stands for Interstellar, and the number 3 meant this was only the 3rd such object ever confirmed in human history, after a strange, cigar-shaped visitor called Oumuamua in 2017, and a more ordinary-looking comet named Borisov in 2019. Astronomers later combed through archived sky survey images and found faint traces of the object reaching back to mid-June, meaning it had been sitting quietly in the data the whole time unnoticed until someone finally knew what to search for. At the moment of discovery, 3I/Atlas was already moving at roughly 137,000 miles per hour, and it was still well outside the orbit of Jupiter. That speed alone told researchers this was not a local object. Comets that belong to our own solar system get flung around by planetary gravity, but they do not arrive already moving that fast from that far away. Something else, some other star system entirely, had accelerated this thing long before it ever encountered our sun. By later in 2025, astronomers had worked out its orbital eccentricity, a number describing how stretched an orbit is, and it came out to roughly 6.1, making 3I/Atlas more extreme in its trajectory than either of the 2 interstellar visitors that came before it. Of the 3 confirmed so far, this one is moving through the solar system on the least bound, most aggressive path of the group. It is worth pausing here to appreciate how different each of those 3 prior visitors actually turned out to be, because it puts this discovery in proper context. Oumuamua, spotted in 2017, tumbled through its brightness cycle in a way that suggested an elongated, almost cigar-like shape, showed no visible coma or tail at all, and displayed a faint but measurable acceleration that could not be fully explained by gravity alone, a mystery that generated its own share of headlines at the time. Borisov, found in 2019, behaved much more like an ordinary solar system comet, with a conventional dusty tail and chemistry that mostly matched what astronomers already expected. 3I/Atlas does not fit neatly into either template. It has an obvious active coma, like Borisov, but a chemical fingerprint and an age that place it in an entirely different category altogether. Before we go any further, if the kind of story that actually explains what scientists measured, instead of what a headline exaggerated, is what you come here for, go ahead and subscribe now, because the way this discovery unfolded across 4 different space telescopes is genuinely one of the strangest sequences in recent astronomy, and you will not want to miss where it leads. Roughly 3 weeks after the initial discovery, NASA turned the Hubble Space Telescope toward the incoming object. And this is where the story most people never actually hear begins. Hubble could not see the solid nucleus of the comet directly because a fuzzy cloud of gas and dust called a coma was surrounding it, the way it does with most active comets warming up as they approach a star. But by carefully modeling that glow, astronomers were able to put boundaries on the size of the icy body hidden underneath. Their initial estimate placed the nucleus somewhere between 1,400 feet and 3.5 miles across, an enormous range of uncertainty that tells you something important right away. This object was extraordinarily hard to pin down because, unlike anything studied close to home, there was no prior data to compare it against, no history, nothing familiar to calibrate the models on. What Hubble did manage to capture, though, was striking on its own. The images revealed a teardrop-shaped cocoon of dust streaming off the comet's icy nucleus, yet noticeably missing the long, distinct tail that typically trails behind an active comet at this stage. Astronomers studying the images noted that the coma looked unusually puffy and well-developed for an object still so far from the Sun, which was the first hint that something about this comet's behavior did not match the standard playbook. An amateur astronomer who processed some of that early Hubble imagery into short time-lapse sequences later commented that even with cosmic rays peppering the frames, the comet's coma looked remarkably full and defined, giving the public one of its very first genuine glimpses of what this ancient traveler actually looked like as it raced through the outer solar system. That mismatch only deepened once other instruments joined in. Data from NASA's Transiting Exoplanet Survey satellite, originally built to hunt for planets around distant stars, was later found to contain faint traces of 3I/Atlas from months before its official discovery. Those archived observations showed the object was already bright and active when it was still roughly 6 astronomical units from the Sun, well beyond the orbit of Jupiter, a distance at which most solar system comets remain frozen and completely inert. Something about this particular visitor was already venting gas and dust into space at a distance where the Sun's warmth should have been far too weak to trigger that kind of activity. Whatever was happening on its surface, or just beneath it, was starting earlier and running hotter than anything researchers expected from a body that had supposedly spent billions of years drifting through the extreme cold of interstellar space. As 3I/Atlas moved closer to the Sun and continued warming, both the James Webb Space Telescope and NASA's newer SPHEREx mission got their own look at the gases pouring off it. In a typical solar system comet, you would expect water vapor to dominate that outgassing, since water ice is the most common frozen material comets carry. That is not what these instruments found. The coma of 3I/Atlas was overwhelmingly carbon dioxide, making up roughly 95% of the detected gas, with water accounting for only a small fraction. A carbon dioxide-dominated coma at this distance from the Sun is genuinely unusual. It suggests the object formed somewhere extremely cold, far colder than the region where the comets in our own solar system originally condensed, in a part of some ancient stellar disk where carbon dioxide ice could survive while water ice would not. Researchers who studied this detection described it as strong evidence that 3I/Atlas came from a formation environment fundamentally different from anything in our solar neighborhood. That single measurement alone reshaped how scientists thought about the object, shifting it from an intriguing curiosity into something closer to a genuine sample of chemistry from another corner of the galaxy entirely, sealed inside ice for longer than most stars in the sky have existed. SPHEREx followed up months later and confirmed organic molecules were present within the coma as well, adding yet another layer to an already complicated chemical picture, and giving researchers a second independent instrument confirming what the first had already suggested. Then, in February 2026, a research team at Auburn University published findings that added a genuinely startling detail to the story. Using NASA's Swift ultraviolet optical telescope, they had observed the comet during 2 separate visits back in July and August of 2025, tracking the faint ultraviolet glow of a molecule called hydroxyl, which traces water vapor escaping into space. Each of those observations combined dozens of short exposures stacked together to reach total integration times of more than 2 hours in ultraviolet light alone, allowing Swift's vantage point above Earth's atmosphere to detect emissions that are normally invisible from the ground. What they found was that 3I/Atlas was releasing water at a rate of roughly 40 kilograms every single second, while it was still far from the Sun, much farther out than the distance at which most comets typically switch on and begin releasing water in meaningful quantities. That is an enormous amount of material to be shedding at that kind of range, and it forced researchers to reconsider just how much frozen volatile material this object might actually be carrying, and how differently it was behaving compared to anything born inside our own solar system. If you are finding this as strange as I did while putting it together, take a moment to hit like on this video right now. It genuinely helps this kind of careful, sourced science content reach more people who would actually want to hear the real version of the story instead of the exaggerated one. The age of this object is where the picture became even more extraordinary, and it took months of careful follow-up work to properly nail down. Early estimates, based purely on the comet's orbit and the population of stars and the part of the galaxy it appeared to come from, suggested an age of around 7 billion years, already older than our entire solar system. The real confirmation came later, once Webb's instruments observed the comet on multiple dates after it had already swung past the Sun and was heating up from fresh solar exposure. Researchers led by a scientist at NASA's Goddard Space Flight Center used that data to measure the ratio between 2 forms of carbon in the gas, ordinary carbon-12 and the heavier isotope carbon-13. Almost all the carbon in our galaxy is forged inside stars more massive than our own Sun, And the balance between these two isotopes shifts gradually over cosmic time as generations of stars are born, live, and eventually enrich the surrounding galaxy with new material. And what that research team found was a carbon isotope ratio containing far less carbon-13 than anything ever measured in our own solar system or in the young planet, forming disks surrounding other nearby stars. Working backward through models of how the galaxy's chemistry has changed over billions of years, they concluded the object most likely accreted its ice somewhere between 10 and 12 billion years ago, during an early, intensely active period of star formation that astronomers sometimes call cosmic noon. For context, our own solar system is roughly 4.6 billion years old, and the universe itself is approximately 13.8 billion years old. This particular visitor may have already been drifting through the empty space between stars for longer than our sun has existed at all. One researcher involved in the work told reporters it might be, in his own words, the oldest object ever observed passing through our solar system. Alongside that carbon isotope discovery, instruments also picked up something unusual in the water the comet was releasing. The ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen was significantly higher than what is typically found in solar system comets, with some analyses putting the enrichment at roughly an order of magnitude greater, and other estimates going even higher. That kind of deuterium enrichment tends to form only in extremely cold environments, colder than about negative 243 degrees Celsius. Combined with the carbon isotope data, it painted a consistent picture, an object that formed somewhere unusually frigid, and unusually long ago in a part of the galaxy current models associate with what is called the galactic thick disk, an older, more scattered population of stars than the flatter, younger disk our own sun belongs to. One astronomer who studied the comet extensively, but was not involved in that particular research, told reporters that before these measurements, getting this level of detailed chemical information from an interstellar object was something scientists could genuinely only dream about. That would already be enough to make 3I/Atlas one of the most significant discoveries in recent planetary science. But the detail that actually pulled it out of specialist journals and into worldwide headlines came a little later, and it is the part of this story where things get genuinely strange. In October 2025, a research team using a powerful spectrograph on the European Very Large Telescope in Chile detected something in the comet's coma that nobody was expecting. A plume of nickel gas, later corroborated by additional observations from the Keck 2 telescope in Hawaii. On its own, detecting nickel vapor is not shocking. It has been seen before in a handful of solar system comets, including Borisov, the previous interstellar visitor. What made this detection different was what was conspicuously missing. Every previous time nickel vapor has been detected venting from a comet, it has been accompanied by iron vapor, because the two metals are forged together inside dying stars and supernovae, and they travel through space bound to each other as what researchers sometimes call cosmic twins. In 3I/Atlas, the nickel signal was strong, and the iron signal was nearly absent entirely. Astronomers scrambled to explain how that was even physically possible. Comets are generally far too cold at these kinds of distances from the sun for solid metal grains to sublimate directly into gas, so something had to be releasing the nickel through a different chemical pathway, most likely a nickel-bearing molecule that breaks apart more easily under weak sunlight than whatever compound is holding the iron in place. There's a known natural process involving compounds called nickel carbonyls that could, in principle, explain low-temperature nickel release without any accompanying iron. And most of the astronomers studying 3I/Atlas consider this the most likely explanation, alongside other refractory nickel-bearing minerals that may simply behave differently than iron-bearing ones when heated at extreme distances from the sun. But researchers were honest that at the time of these observations, nobody had fully confirmed which specific compound was actually responsible, and several published papers described the detection using words like extremely puzzling, because nothing in the solar system comet record looked quite like it. To understand why this distinction matters so much chemically, it helps to know how nickel and iron normally behave inside a comet. Both metals typically start out locked inside solid refractory dust grains that require intense heat to vaporize directly, heat that simply should not be available at the distances where 3I/Atlas was already showing the signal. If the leading hypothesis holds up under further study, it would represent a previously undocumented category of natural comet chemistry, rather than any evidence of something manufactured. One prominent voice in this story, Harvard theoretical physicist Avi Loeb, who has spent much of his career searching for potential signs of extraterrestrial technology, pointed out publicly that nickel, without accompanying iron, is otherwise mainly associated on Earth with an industrial refining process. He raised the possibility, repeatedly, that this anomaly could indicate something artificial, and he also pointed to the comet's trajectory, which passes unusually close to the plane in which the planets orbit, as another data point he considered worth flagging. It is important to be clear that this remains a minority position within the scientific community. The overwhelming majority of astronomers working directly on 3I/Atlas, including the teams who made these specific detections, favor natural chemical explanations rooted in the comet's unusual, ancient, and extremely cold formation environment, not a manufactured origin. Researchers have also pointed out that faint traces of this same nickel-dominant pattern, though far less pronounced, were spotted in Borisov as well, which suggests this could be a genuine feature of comets that formed outside our solar system rather than something unique to this one object. The anomaly itself, nickel with essentially no iron, remains real, measured, and not fully explained down to the exact molecule, which is a large part of why this story kept generating headlines through the back half of 2025 and into 2026. The seriousness with which scientists treated this unknown is worth mentioning in its own right. A team of researchers actually pointed the Allen Telescope Array, a radio observatory built specifically to search for potential signals from extraterrestrial technology, directly at 3I/Atlas during its passage through the solar system, systematically scanning across a wide range of radio frequencies for anything that might indicate an artificial transmitter. This was not a fringe stunt. It was a peer-reviewed techno-signature search conducted using the same rigorous methodology applied to any other candidate target. The result was a clean non-detection. No artificial radio signal was found coming from the object. At any frequency, the array was capable of monitoring. It is a small detail that rarely makes the dramatic headlines, but it matters, because it shows that when a legitimate scientific question got raised, however unlikely the answer, the response was not to speculate from an armchair. It was to actually go check with a real instrument and report exactly what was and was not found. The comet's physical shape and mass came into sharper focus only after it had already passed its closest point to the sun. Early observations noted that 3I/Atlas was not developing the kind of long, dramatic tail that sunlight pressure typically pushes off an active comet, which led to speculation about whether its nucleus might be unusually massive or its surface unusually resistant to that pressure. Some early back-of-the-envelope estimates based on that missing tail put the object at somewhere north of 33 billion tons, dramatically heavier than Borisov. Once the comet moved past its closest approach, and astronomers could finally separate the glow of the solid nucleus from the surrounding coma and Hubble's images, taken across multiple visits in late 2025 and early 2026, they arrived at a more refined number. The effective diameter came out to approximately 2.6 kilometers, with an uncertainty of around 0.4 kilometers, narrowing that earlier wide range considerably and confirming this was a genuinely large object by interstellar standards, notably bigger than Borisov, though the more extreme mass claims from earlier speculation were not what the refined measurements ultimately supported. It is worth appreciating just how much work went into reaching that number. Separating the faint glow of a small, solid nucleus from the much brighter surrounding coma, across a distance of hundreds of millions of miles, required stacking dozens of individual exposures, and carefully subtracting out the contribution of escaping gas and dust. A painstaking process that only became possible once the comet had moved far enough past the sun for its activity to calm down slightly. And in December 2025, Webb made another significant discovery in the comet's coma, a robust confirmed detection of methane, a hypervolatile ice that only sublimates at extremely low temperatures, adding yet another data point to the growing picture of just how unusual this object's original chemistry really was. This comet also received a level of direct, close-up scrutiny that neither of the two interstellar objects before it ever got. On October 3, 2025, during its closest approach to Mars, 3I/Atlas passed within about 29 million kilometers of the planet, close enough that NASA's Perseverance rover, along with multiple Mars orbiters and the European Space Agency's own Mars orbiters, managed to capture images of it, marking the closest any spacecraft had ever gotten to an interstellar object. Between October 1st and October 7th, the European Space Agency's ExoMars Trace Gas Orbiter turned its own instruments toward the comet from its position circling Mars, adding a vantage point no ground-based telescope on Earth could ever match. The European Space Agency's JWST spacecraft, already en route toward Jupiter's icy moons, attempted its own observations of the comet as it passed nearby, using its cameras, spectrometers, and particle sensors to add yet another perspective. Because JWST was close to the sun at the time and had to use its main antenna as a heat shield, most of that data trickled in slowly over a low-bandwidth backup antenna, and the bulk of its observations did not actually reach Earth until February 2026, with mission teams still working through what that data reveals as of this year. A first glimpse from JWST's science camera, once it finally arrived, showed a clear tail and visible structure within the coma that ground-based telescopes had struggled to resolve in the same detail. Ground-based observatories joined the effort, too. The Gemini North Telescope in Hawaii captured a detailed image of the comet in late November 2025, processed to correct for the streaking star trails caused by tracking such a fast-moving target, giving the public one of the clearest visual looks yet at what this ancient traveler actually resembled against the background stars. So here is why any of this should matter to you beyond simply making a good headline. Every comet native to our own solar system formed from the same disk of material that built the planets. So studying them mainly tells us about our own local chemistry. 3. I/Atlas is different. It is a physical sample of material that condensed around a completely different star, under different temperatures, at a different point in the galaxy's history, and it drifted here across billions of years without ever being disturbed by any star's heat until it encountered ours. That gives researchers something they have never really had before, a direct chemical comparison point to test whether the process of building icy bodies works the same way everywhere in the galaxy, or whether it varies significantly depending on where and when a star system happened to form. The nickel and iron anomaly, specifically, is forcing cometary scientists to reconsider assumptions about how metals get locked into or released from ice at extreme distances from any star, assumptions that were built almost entirely on a sample size drawn from solar system comets alone. This is not a discovery that overturns existing physics. It is a discovery that gives long-standing models of planet formation their first real external check, using an object that was never supposed to be here for scientists to study in this kind of detail at all. As for where things stand right now, the timeline since discovery has moved quickly, and it is worth laying out precisely. The comet reached perihelion, its closest approach to the Sun, on October 29, 2025, passing at a distance of about 203 million kilometers, just inside the orbit of Mars, with its speed peaking around 246,000 kilometers per hour at that point. After that, it passed near Venus on November 3, 2025, and made its closest approach to Earth on December 19, 2025, at a distance of about 270 million kilometers, roughly 1.8 times the distance between Earth and the Sun. NASA and the European Space Agency have both been explicit and consistent throughout this entire event that 3I/Atlas posed no threat of impact at any stage of its journey through our solar system, and it never came remotely close enough for that to be a realistic concern. After swinging past Earth's distance, the comet continued outward, passing near Jupiter on March 16, 2026, at roughly 54 million kilometers. By this point in 2026, it has receded far enough that it can still be tracked with dedicated instruments, though it continues growing fainter and more distant with every passing month, and researchers expect it to become effectively unobservable to most current ground-based instruments before too much longer.